Hi, and welcome to this video about earthquakes. Today we'll discuss what an earthquake is, the mechanics behind how they happen, where they happened, and the damage earthquakes cause. Let's get started. Before we get into what an earthquake is, we need to go over the mechanics of how they happen. Earth's crust is divided into many different sections called tectonic plates. Some are small, some are large. This will give you a better idea of just how large these plates are. As you can see, many of the tectonic plates follow the shape and size of the continents. What you'll also see are several smaller tectonic plates, like the one off the coast of California called the Juan de Fuca plate. We'll come back to this one later. The most important takeaway here is that these plates are constantly moving toward, away from, or past one another all the time. The speed at which these plates move varies from excessively slow to extremely fast and abrupt, which increases seismic activity. Along the borders where the plates come together, we have plate boundaries. Now, there are three different kinds of plate boundaries: convergent, divergent, and transform. Convergent boundaries are where two tectonic plates are merging, colliding, or joining together. An example of a convergent plate boundary is at the tall Himalayan mountain range where the Indian plate collides with the Eurasian plate, pushing Earth's crust upwards. Look at the cross-section here. The two colliding upward arrows indicate the movement of the Indian plate and the Eurasian plate. Along the dotted line is the Himalayan mountain range. Another example of a convergent plate boundary is a subduction zone where we find deep ocean trenches like the Mariana Trench, the deepest trench known on Earth. At this type of boundary, two plates are also moving towards one another, but instead of both moving upwards, one will slide beneath the other. This movement of one plate beneath the other is called subduction, hence the name subduction zone. At this type of convergent plate boundary, a more dense oceanic plate slides beneath a less dense continental plate. As you can see in this image, the deepest point in the ocean is found where the oceanic plate is subducting under the continental plate. This area, as shown in the image, is called a trench. The next type of plate boundary is a divergent boundary. You'll find this when two plates are moving away from each other, like at a mid-ocean ridge. What you're looking at here are two oceanic plates moving away from one another and fresh ocean crust being solidified by cooled magma that comes to the surface between the two. Lastly, a transform boundary is where two tectonic plates are sliding horizontally past one another. An example of a transform plate boundary is along the San Andreas Fault. This is where the North American plate and the Pacific plate are sliding past one another off the western coast of California. There's a lot of tectonic business going on in California. You have the North American plate, which is moving southeast, and you've got the Pacific plate, which is moving northwest. In addition, you've got this little sliver of the Juan de Fuca plate, highlighted in purple, that is moving both northeast and also subducting beneath the North American plate. California is a hot spot for earthquakes because what lies beneath is in constant motion. All right, so now that we've talked about the tectonic plates and a little bit of where they move, let's talk about why they move. As previously mentioned, tectonic plate boundaries move along faults. Faults are fractures in the Earth's crust and are associated with building stress at plate boundaries. When enough stress builds along these faults within the Earth's lithosphere, it eventually has to be released. We'll come back to different types of stress in a minute, but first, we need to learn about the different types of faults. Types of faults include normal faults, reverse faults, and strike-slip faults, each of which has its own unique plate boundaries. Normal faults are associated with divergent plate boundaries, like seafloor spreading or continental rifting. The side that slides downward is called the hanging wall because it looks like it is reaching or hanging out over the side. The opposite side is called the footwall. When the hanging wall is moving upward against the footwall, we call it a reverse fault. When the slabs of rock are sliding past one another with no up or down movement, it's called a strike-slip fault. In this case, there's no hanging wall or footwall. Earlier, I mentioned there are different types of stresses. Each type of fault is associated with its own type of stress. Take a look at the top left. You see two plates moving away from one another with tensional stress. Think of a game of tug-of-war. When the opposing teams pull the rope in contrasting directions, tension is created. What type of fault is this tensional stress associated with? A normal fault. The top right shows compressional stress. Two plates are compressed together at a convergent plate boundary along a reverse fault. Lastly, we have shear stress, where two plates slide past each other along a transform boundary, and a strike-slip fault. After these tensions build up along the fractures in Earth's crust, all that tension has to be released. This is what we know as an earthquake. An earthquake is defined as violent ground shaking caused by the sudden and rapid movement of portions of the lithosphere moving past one another. Along the fault plane, the exact point at which the earthquake originates within Earth's crust is called the hypocenter, or the focus. The corresponding point directly above the Earth's surface is called the epicenter. Can you tell what kind of fault is this? Look at the arrow movement along the fault plane. The footwall is sliding down while the hanging wall is sliding up. This means it's a reverse fault. The hypocenter can be very deep within Earth's crust or very close to the surface. An earthquake with a shallow hypocenter tends to do more damage than a deeper earthquake because the damaging seismic waves have less distance to travel to reach Earth's surface. There are two types of waves associated with earthquakes, P waves and S waves. Primary or P waves compress and expand the material through which they pass. Think of pushing a spring toward and away from a wall. The waves move in the same direction of motion. Secondary or S waves, however, move perpendicular to the direction of motion and cause material to oscillate side to side. Think of battle ropes at the gym. The wave is moving horizontally, but the ropes are moving up and down. As you can imagine, it's the S wave that does much more damage than the P wave during an earthquake. This is because the S wave has a greater amplitude. I'll show you what I mean in just a minute. To detect these waves and record the movement of the Earth, we use an instrument called a seismograph. Seismographs actually detect any kind of ground motion, not just earthquakes, so they can record things like volcanic eruptions or explosions. This is an example of a seismograph. You can see here that, as I said before, S waves definitely do more damage. This is a map from the Global Seismographic Network that shows where each of these seismograph stations are located. They're evenly dispersed throughout the globe so that scientific positioning techniques can be used to determine the location of the earthquake's epicenter. Now let's talk about destruction. The damage earthquakes can cause is dependent on a variety of factors, including proximity to the epicenter, duration of vibration, composition of the ground beneath the structures, and the nature of building materials or construction practices of the region. Areas affected by earthquakes are also at risk for secondary hazards after the rumbling has subsided. There are two measurements used to describe the size of an earthquake: intensity and magnitude. The intensity of an earthquake is a measure of the shaking produced by the earthquake, which is based on property damage. The magnitude of an earthquake is an estimate of the amount of energy released at the hypocenter. Remember, the hypocenter, also called the focus, is the exact point beneath the Earth's surface where the earthquake originates. The current magnitude scale, the Richter scale, is a logarithmic scale with each unit of magnitude increase representing a 32-fold increase in energy released. In other words, A 3.0 magnitude earthquake releases approximately 32,000 times more energy than a 2.0 magnitude earthquake. We normally can't feel an earthquake with a magnitude of 2 or less, while a magnitude of 8 or greater causes widespread destruction. An area closer to the epicenter of an earthquake will face more violent shaking due to the S waves traveling a shorter distance. A longer duration of vibrations due to the earthquake will result in more damage to structures. Check out this clip of a very destructive 9.1 magnitude earthquake in 2004. You'll notice the shock waves reach areas of the globe far away from the epicenter. Another thing that can have a profound effect on the damage that results from earthquakes is the composition of soils and sediments beneath structures. Soft sedimentary rock like sandstone or siltstone amplifies the seismic waves more than solid bedrock, which results in more damaging S waves. Loosely packed and waterlogged sediments can also behave as a fluid during vibrations of an earthquake. In addition to building damage done by the shaking itself, there are many secondary disasters that can happen after the shaking stops. Landslides can occur after earthquakes when areas with steep slopes have loosened soil as a result of the movement. Due to broken gas and power lines, fires can flare up, adding to the damage already done. Another side effect of earthquakes can happen when an earthquake has an hypocenter under oceanic crust. In this case, it is very likely that a tsunami will result. A tsunami is a series of large ocean waves, and most are generated by displacement from a reverse fault found at a subduction zone. The hanging wall slips upward and displaces a significant amount of water. The water has to go somewhere, so it races away from the epicenter in every direction. Tsunami waves move very quickly in the open ocean and are very small, a few centimeters or inches tall. However, when nearing the shore, the waves slow considerably and grow to be enormous, some over 90 feet tall. The inundation of water that is brought inland by tsunami waves increases the damage already done by the earthquake. Okay, that was a ton of information, so let's go over a few questions to make sure you remember it all. Number 1, what is the correct combination of plate boundaries and faults? A, divergent, normal, B, transform, reverse, or C, convergent, strike slip? The correct answer is A, divergent, normal. At a transform plate boundary, you will have strike slip faults, and at a convergent plate boundary, you will have a reverse or thrust fault. Number 2, what small tectonic plate is subducting beneath the North American plate off the western coast of California? A, the Pacific plate, B, the Nazca plate, C, the Juan de Fuca plate, or D, the Scotia plate? The correct answer is C, the Juan de Fuca plate. The Pacific plate is subducting along the Ring of Fire, but it is just sliding past the North American plate. What type of plate boundary causes tensional stress? Convergent, divergent, or transform? The correct answer is B, divergent. A convergent plate boundary causes compressional stress, while a transform boundary causes shear stress. I hope this review was helpful. Thanks for watching, and happy studying.